Hello, welcome to another module of this course, NPTEL MOOCs program, Microwave Integrated Circuits. In the previous modules in this week, we have covered the design aspect using gain circles. So in those modules, we covered how to achieve a particular gain, whether it's a transducer power gain or available power gain or operating power gain. In this module, we will be covering another important aspect of amplifier design, which is the noise aspect. So in the first part, we will be covering what is noise, how to characterize noise, and in the second part, we will be discussing about noise circles and how to achieve a particular noise figure, and then we will also see what is a noise figure, what is the term noise figure mean, and how to achieve if we have a given noise figure specifications and how we can achieve that using noise figure circles. So first question is, what is noise? Noise, if you have any idea about statistics, then noise is a random process. What do we mean by random process? First, let us see what is a random variable. A random variable is a quantity which doesn't have any fixed value, unlike deterministic quantities, say a voltage. It has, at a particular instant, it will have a definite value. But say noise voltage, if we say, then it doesn't have any particular value. Instead, what we can characterize it is with some average or moments or what we call probability density functions. Now, an ensemble of such random variables, over time, if time is also now a variable, then such a process is called a random process, and noise is such random process. Now, how to, as I said, you cannot have a deterministic value. For example, I say that the voltage, if you measure the voltage of a battery, you might find it to be 2 volts. Then you say that the voltage of the battery is 2 volts. But on the other hand, say noise voltage, at an instant, it may not be the same value. It keeps on varying. The value of the noise voltage keeps on varying. But then the average value of, if you find out the average of the noise voltage, then that remains constant. So that is how we characterize noise, that even though we cannot exactly specify what the real voltage will be at a particular instant of time, we can say what the average will be over time. So in that sense, there are two types of average actually. One is what is known as the time average. That is represented by this symbol, and it is defined as like this. So it is like the average of the noise voltage or any other random process with time. On the other hand, another kind of average that we can define is what is known as an ensemble average. Here, instead of at a particular instant of time, what is the average value that the random process takes? So the representation of ensemble average is by this symbol. Similarly, these are the time average and ensemble average. If we consider the power content in any signal, whether it is noise or any other random process, Then two other definitions that we can use is what is known as mean square power. Now the mean square power can be defined in terms of its variation with time, just like the time average that we define. Or in terms of the ensemble, that is now here this term, this Pn, both for the ensemble average that I discussed in the previous slide. In this slide, I was discussing about ensemble average. I wrote this equation. This Pn represents the probability density function. It is like what is the probability of finding a particular value of n among the various possible values that n can take. Probability density function. Here also, in the case of this mean square power, the ensemble average, this Pn represents the probability density function, or simply PDF. Now, for our purpose, when we define noise, the average value, that is the ensemble or ensemble average or the time average, both are equal to 0, and so is the case with the mean square power. Now, time average, for a stationary random process, another quantity that is frequently discussed is what is known as the autocorrelation function. Which is given like this, and I'll just describe in a moment why this autocorrelation function is so important. This is a definition of autocorrelation function, which is the same function x, which is a kind of relationship between x at t and x of t plus tau. It is at a time spacing. x1 represents x of t, x2 represents xt of tau. And the importance is that if we take the Fourier transform of this function, is the autocorrelation function, then we get what is known as the spectral density. Where this xt is given as as I said, xft is a measurable quantity known as the spectral density. This is something you can actually measure using a device, using an instrument called spectrum analyzer, and this is the Fourier transform of this RT that I just defined. Now, ideally, what we see when we when we take any device or if we try to measure the noise power, then there are various kinds of noise power. One of them, various kinds of noise power that we see depending on what kind of spectral density they have, what kind of spectral distribution they have. One of them is what is known as a thermal noise. Now this thermal, let me write it properly. Thermal noise has a distribution like this. Okay. The autocorrelation function for this thermal noise is given by this equation. Okay. This thermal noise is also known by the term as white noise. Now, it can be shown that for a resistor, a simple resistor that we have, if it exhibits, if it has, if we consider the noise power that is present inside the resistor, then the noise power can be given by this equation. And this available power value is given by Pn is equal to Vn square by 4R, from which this noise voltage value can be found out to be 4 kT R delta F. So, this is the equivalent noise voltage that is always present when you have a resistance. The derivation can be seen, the detailed derivation can be seen in the book by Gonzalez. But just I want to impress on you that a resistor is not just a simple resistance as we have known from circuit theory. There is also a source kind of associated with it. The source does not have any direction, that is, it is difficult to say which is the positive and negative, it can't say it like that. All we can say is that there is a power associated with the source, and that power value is given by this equation, from which this equivalent noise voltage is given by this equation. Now, that was the basic noise definition. But what about our two-port microwave devices? How do we characterize the noise associated with our two-port microwave devices, or in other words, the noise of an amplifier? Now, for a two-port network like this, so for a two-port circuit, say this is a noisy two-port circuit with various noise elements present. From that, if we have to go to a noiseless circuit, then we make a transformation like this. And how the derivation of the values of this Vn and In is given in Appendix L of the book by Gonzalez. Please go through it. So, for example, if we can take up various noisy devices like say MOSFET. Let us see a simple MOSFET, which is an active device and has some noise associated with it. In fact, uh, a simple MOSFET has a circuit like this. Now, the equivalent noise circuit for this MOSFET can be given like this. This is noiseless, and this value of this In square is given by and the value of this Vn square is given by now and related term that is often associated with two-port networks is what is known as a noise figure. Now let us see what is a noise figure. What does the term noise figure mean? Suppose you have a two-port network. There is say an input signal and an output signal. The noise figure is defined as SNR in upon SNR out. Note it's not SNR out upon SNR in, it is SNR in upon SNR out. Unlike other terms, other gain terms where you always have the output term at the numerator and the input term at the denominator. That is not the case here. Now SNR in is given by S in upon N in T. Here S in is the signal power of the input, that is the part of the input without the noise, and N in is the noise power at the input, that is only the noise power, and SNR out is equal to S out upon N out. Now this T that is there, it's just to signify that noise is associated with heat or the temperature, and it's a function of temperature. So the SNR, without changing anything in this circuit, if you change the temperature, the N in and N out will change, and therefore the SNR values will also change. So F in Ft, this noise figure F is given as SNR in upon SNR out, which I can write as S in upon N in as a function of T multiplied by N out over S out as a function of T, this is equal to n out over n in. Now I am removing the t term upon GA. So GA is nothing, we are assuming that this is the the actual power delivered to the load upon the power available from the network. So that's why this S out upon S in is equal to GA, and with so GA is equal to S out over S in. Now some of the properties of noise figure are that this F is always greater or equal to 1. It cannot be less than 1, because in any two-port network, the SNR of the input will always be greater or at best equal to the SNR at the output. There will always be some out noise contributed by a network, hence the signal quality will either remain the same or will be a little bit degraded at the output. Hence SNR in can never be lesser than SNR out, therefore F will always be greater or equal to 1. F is equal to 1 for zero noise power added, that is when a network is perfectly noiseless, it contributes absolutely zero noise, then only then F will be equal to 0. So one of the properties of this noise figure for a passive device. Now we saw that what is the definition of SNR for an active device. For a passive device, this noise figure, we can show that this noise figure is simply equal to the attenuation. That is, if FL is the attenuation, so attenuation is the reverse of gain. If instead of gain we get attenuation, then we can show that that the noise figure will be equal to the attenuation. Now one other property of noise figure is if we have a cascade of networks, say two networks, say this has noise figure value F1 and available gain value GA1, this has available gain value GA2 and noise figure F2, then what will be the overall noise figure of this system? It can be shown that the overall noise figure F12 will be equal to F1 plus F2 minus 1 upon GA1. Suppose there was another stage here with a noise figure F3 and GA3, then the value of the total noise figure, that is F1 to 3, would be F3 minus 1 upon GA1 multiplied by GA2. So what we see here is that when we have a cascade of elements connected, the highest noise contribution to the overall noise figure is from the first stage. The other subsequent stages are scaled down by the value of the available gain of the preceding stage. So that's why when we have a receiver connected to an antenna, the first stage is often what is known as a low noise amplifier. The purpose of the low noise amplifier is to boost this small power signal received from the antenna without contributing too much noise. That's why LNA is supposed to have a very good noise figure. In fact, it should be less than 2 dB. And the purpose of LNA is not to provide power gain so much, but to ensure that the signal is amplified from the extremely low values received low power values received by the antenna to a value which can be used by subsequent stages. And this LNA, because the reason this LNA has to have a low noise figure is because of this equation. That is, it doesn't really matter what the subsequent stages, what is the noise contributed by the subsequent stages, as long as the noise contributed by the first stage, that is the LNA, is less, the overall noise figure of this chain of elements will also be low if the first element has a noise figure, low noise figure. And for a special case for this is the case when we have a gain stage connected to an attenuator. So suppose we have or a attenuator connected in cascade with a gain stage. So say this is an LNA and this is a filter. Now this is a passive stage. So it doesn't have any gain, instead it has an attenuation L. I said the noise figure of a passive device, that is one which attenuates a signal, is same as the attenuation. But this LNA will have, say, a gain A2 and a noise figure F2. And it can be shown that the total gain, total noise figure is simply L multiplied by F LNA. Or in terms of dB, it is L in dB plus F LNA, that is the noise figure of the LNA in dB. A related concept is what is known as a noise measure. Noise measure is a quantity which is introduced because of the problems in determining which stage contributes more. When this problem arises especially when we have two cascade stages. Suppose we have one stage GA1 and F1, another GA2 and F2, another GA2 first, F2 first, and then followed by GA1 and F1. Now which one, if I say the overall noise figure for this case is F12 and the overall noise figure for this case is F21, which will be the configuration that gives the lower overall noise figure? That is, if I want to have, say, F12 lesser than F21, then F12, as just from the formula that I gave in the previous slide, will be given like this, and F21 will be given like this. Now suppose the problem with this equation is that this has elements of F1 and F2 are mixed on the LHS and RHS. Instead, this equation can be rewritten as, if I rewrite this equation, the same equation like this, that M1 equal to F1 minus 1 upon 1 minus 1 upon GA1 is lesser than F2 minus 1 upon 1 minus 1 upon GA2, and say this I call M2. If M1 is lesser than M2, note both M1 and M2 have terms related to the first stage and the second stage respectively. If M1 is lesser than M2, then we can ensure that F12 will be lesser than F2. And these quantities, this M1, M2, are called noise measure. So we have noise figure and then noise measure. So in summary, in this module we covered the basics of noise. What is noise, how to characterize noise mathematically, and then what is noise figure and how to find out the noise figure of a chain of stages, which element contributes most to noise figure, and then the concept of noise measure, that is when we have two elements or various elements in cascade, how to stack, how to put them in cascade so that the lowest, so that the chain will have the lowest noise measure of the various combinations, noise figure of the various combinations possible. And therein we found out that a new term called noise measure. In the next module, we'll discuss about noise figure circles. We'll see that if we set the noise figure value of a circuit to a certain value, so if we want to obtain a particular value of noise figure in a two-port circuit, then the locus of gamma s will be a circle, and that circle is known as a constant noise figure circle, and using that we can design a particular value of noise figure that we want to obtain in the same way that we did with the constant gain circles. So that will be covered in the next module.